right, welcome to the second morning session. And Mike Zalatel tell us about chiral superconductivity and fractional quantum insulator.
Hey, thanks so much. Thanks to Mike and Ashvin and Natty for having us here. So I'm going to be talking about topological phase transitions between a chiral superconductor and a fractional quantum Hall state, motivated initially by some really amazing experiments in 2D materials. This was a project that was actually started by Taiga, and he finished it and then told me about it. So I had very minor contributions to it, but I find it quite exciting. So my introductory motivation for this audience is a little bit different than other ones, and I'm going to motivate it in terms of the parton construction, which gives a really nice way to both talk about fractionalized phases, but importantly, to think about phase transitions between them. So if we were going to discuss the fractional quantum Hall effect, one way we might describe it is to take the electron, split it into 3 partons. Then I can imagine a sort of mean field description where the partons enter into 3 different phases of matter, but they must interact with each other through these emergent gauge fields, in this case, a little a and a little b, to make sure that this is a gauge invariant description. And then using this, we can generate a large number of different topological phases by just positing that the 3 partons enter into insulating states with different band structures. And the important thing about their band structure is going to be what is the Hall conductance, or the Chern number of the band they enter into. So to get the Laughlin state, you can think of that as the cube of 3 integer quantum Hall effects. So I'd give all 3 partons Chern number 1. But then you can consider transitions where you change the Chern number of one or multiple of them. So for example, if one of the partons goes from Chern number 1 to 0, that then describes a trivial insulator, and you can keep going to get into quantum Hall, fractional quantum Hall. This is in a way is just the usual description of the Jane sequence, where you can think of these 2 partons as attached to flux. This parton is then the composite fermion, and the composite fermion occupying different number of lambda levels gives us the usual Jane sequence. But you can do more interesting things. You could start changing, for example, the parton, also the Chern number here. That would give an integer quantum Hall. And surprisingly, you can go beyond quantum Hall states. If you go to this configuration -2, 1, -2, which I'll discuss, that actually gives you a superconductor. Or if you do -2, 0, 1, you get a chiral spin liquid, and you could consider many others. So this gives a really convenient framework. I mean, there's other types of partons you could do, but you can see you can get many different possibilities here. So the interesting thing then is it then gives us a way to talk about possible continuous phase transitions between these different topological states. And the basic physics is you imagine the partons have some emergent band structure. So you can imagine this is maybe the band structure for the first parton. They have a chemical potential, say here, so they're filling the lowest band. And then you can imagine as you change a parameter in the Hamiltonian, which is driving the transition, that there's this phenomena of band inversion, where the 2 bands touch. When they touch, you get an emergent Dirac fermion, and then it can reopen. So you can think of the band inversion as just a sign changing of a Dirac mass. Now, the interesting thing about that is that whenever you have a sign changing of a Dirac mass, that leads to the transfer of Chern number or Hall conductance from one band to the other. So for every Dirac point, you're going to transfer a Hall conductance of 1 between the 2 bands. And so if your chemical potential sits in the middle, you've then changed the Chern number of the parton. And in our setting, we can generalize this. Oftentimes, there's going to be lattice or point group symmetries, which can make it generic for these band touchings to occur at multiple points in the parton Brillouin zone. And so if ND of them touch, you'll have ND Dirac points, and then the Chern number will change by ND. So this is a nice figure taken from Barkeshli and McGreevy's paper on this. When we then have the parton description, we can then generate a kind of map of possible phase transitions between these topological phases, basically parameterized by what are the masses of the different Chern numbers, and then talk about various continuous phase transitions. So just as an example of what the resulting theory is at the transition, let's consider a case here where I imagine a phase transition between the 1/3 Laughlin state and its particle conjugate, the 2/3 state. In this description, that comes from one of the partons having a 3-fold band touching. And so at the critical point then, if you want to ask what's the theory which describes this, the first parton effectively is now described by 3 Dirac points. And when you work out the effect of integrating out the other partons, you find that there's no leftover Chern-Simons term for the emergent gauge fields. And you'll then actually have pure QED3, so just QED3 with a emergent Maxwell term and no Chern-Simons is the description of this phase transition. This was discussed in this collaboration with Yin Chen and Ashvin and Chong here. So just thinking about this talk, I realized I've now thought about these sorts of transitions from a bunch of independent motivations, actually starting from experiment. So like this particular one I just talked about was motivated by experiments in graphene on HBN, where you have these Moiré potentials, and there was an interplay of quantum Hall physics and Moiré potentials, and we could see evidence of the location of somewhere there is close to a phase transition like this, and so then we discovered it, looked at it numerically here. Recently with Ashvin, we were thinking about phase transitions between the integer quantum Hall effect and a Mott insulator, the chiral spin liquid, where we were able to show there's a concrete model where there's a continuous phase transition, and then talked about anion superconductivity. What I'm going to talk about mainly today is this possibility of a phase transition between a 2/3 fractional quantum Hall effect and a superconductor. With Ashvin, we also worked on a similar one that occurs in quantum Hall bilayers, motivated by some experiments there. And then Taiga also has a nice work with Sentel doing the simplest version of this that was, I don't know if it was first proposed, but in McGreevy and Barkeshley of a phase transition between 1/2 fractional quantum to superfluid. And his numerics there actually show quite nice evidence for the emergence of QED3, though in this case it's coupled to Chern-Simons. So in this talk, I'm going to focus on this one. And hopefully it's of some interest. I want to explain a little bit the very exciting experiment that I think quite a few of us are thinking about that motivated this. So the material that's being pursued by these experimentalists is a generalization of magic angle graphene, but rather than using graphene, they use this TMD, molybdenum ditelluride. They take 2 copies and twist it relative to each other, and that gives this Moiré band structure. And the interesting thing about the emergent Moiré bands is they're both flat and they carry a Chern number. So they're kind of like analogs of Landau levels, but at zero magnetic field. And just this summer, I guess a couple of years ago, the fractional quantum Hall effect was discovered, first at UW. So this is quite amazing. It's a system at zero magnetic field, which spontaneously breaks time reversal. So it forms a magnet, but the interaction with that magnetism and the strong interaction leads to a 2/3 fractional quantum Hall effect at zero magnetic field. So this has been a very long sought effect. And then as the samples improve this summer, there's this kind of amazing phase diagram. This is at zero magnetic field. Conductivity is a function of temperature and the electron density. When you fit at 2/3 filling, you get this quantum Hall effect, so there's zero resistance. Then as you dope that 2/3 quantum Hall effect, there's a phase transition into a superconductor. And there's good experimental signatures that this superconductor is also a ferromagnet of some form. It sort of inherits the same time reversal symmetry breaking as the nearby quantum Hall effect. So this is an example of what line traces of the transport data look like. We're going to be showing here Hall resistance and longitudinal resistance as a function of electron number. Here's the superconductor. It's dissipationless and has no Hall resistance. That's a superconductor. And then you do this tiny change in electron density. Then you have a state which is dissipationless but has a fractional quantum Hall effect. So I think this is quite amazing that these are like the 2 great dissipationless effects in quantum condensed many-body physics occurring right there in the same sample with this tiny change in density. So naturally, it's quite interesting to think about, are they related to each other in some way? And there's kind of 2 fields of thought here. One approach is taking a weak coupling approach, just ignore the fractional quantum Hall physics. One interesting thing about these bands is that they have strong quantum geometry effects like Berry curvature. So people have thought about electron-driven methods of superconductivity like Kohn-Luttinger and ask, what is the implication of quantum geometry on those modes of getting superconductivity? But your starting point is, a Fermi surface, the band geometry of the Fermi surface, and then some weak coupling instabilities. There's another field of thought. This is a nice phase diagram taken by a paper by Sentel recently, where you start out with the quantum Hall. It's more of a strong coupling picture, and then you think of it as doping quantum Hall. So you start with quantum Hall, then you get some dilute gas of anions on top of it when you go away from 2/3 filling, and then you can ask, what are the phases of matter that might result? They could just localize, or there's this idea, I know Zalatel will complain about calling it an anion superconductivity, but it's related to that idea of that they can enter into a liquid state, which ends up being the chiral topological superconductor. So in the current experiment, I don't think they have too much of a way to disambiguate between these two. We don't even know if it's really how continuously they're related to each other, et cetera. So I think it's useful to be able to do some numerics in a model where we can see a similar phase diagram, and then we can interrogate the numerics and try and answer this question of which of these 2 points of view might be at play. So we're going to be doing concrete numerics on a concrete model. And so here's the model we're going to look at. We're not going to try and capture all the details of the band structure of MOTE2, just some of the essential physics. So we consider electrons in a magnetic field, and that kind of reproduces the physics that the bands of MOTE2 carry Chern number. So electrons in a magnetic field. We're going to put on a periodic potential that in this case is going to be a triangular lattice, and then Coulomb repulsion between the electrons. And to kind of mirror the experimental situation, we're going to assume that the strength of the B field is such that there's 2 pi flux within each unit cell. So that means that there's no complicated Hofstadter butterfly physics. What this periodic potential does is it takes the lambda levels we know and love, and it just broadens them and gives them some dispersion like this. Okay, so I now think of this as my model for MOT2, where I have a set of Chern bands, and I'm going to sit at a chemical potential fractionally filling this Chern band, but it now has a bandwidth tunable via the depth of the Moiré potential. And we want to know what is the phase diagram of this system. So when we look at the phase diagram, we're going to consider 2 axes. We're going to start at 2/3 filling without a Moiré potential. That is literally just doing usual quantum Hall physics, and we know we're going to get a 2/3 Laughlin state. And then we can ask what happens when we dope the Laughlin state or put on this periodic potential so that there's competition between bandwidth, dispersion, and the interactions. And so when we treat this model with numerics, this is kind of an overview of the phase diagram we think we see, though really we've most concretely studied it in the undoped case here, or most comprehensively. We see clear evidence for a phase transition between a fractional quantum Hall state, a superconductor, and a metal as you change up the bandwidth. I mean, it certainly makes sense that eventually it's going to be a metal. When there's very large bandwidth, you just form a Fermi surface. But the amazing thing is that there's a superconductor, a chiral superconductor intermediate between them. And as far as I know, this is the first numerical evidence for obtaining a spin polarized superconductor where you're just starting with Coulomb repulsion and some dispersion. Okay, so let me just do one slide on the numerical method we use to solve it. So the basic idea is we start out with electrons in a magnetic field with a periodic potential, and we do the usual trick of quantum Hall numerics where we assume that the interaction is small compared to the cyclotron gap, so it's like a low mass approximation. And then we just project out the higher lambda levels, so we now have a problem with a finite Hilbert space dimension. For the interaction, we try and be somewhat realistic. We consider the kind of interaction you'd have from these 2 DEGs. It's like a gate scream Coulomb potential, or we can be more phenomenological and consider just contact repulsion. Then to solve it numerically, we take this 2D problem and we wrap it onto a cylinder. So we use periodic boundary conditions where you have somewhere between 3 and 8 of the Moiré potential lattice spacings around it. And then we use this convenient effect that when you have electrons in a magnetic field and ask what do the single particle states look like, they form these Landau gauge orbitals, which are localized along the cylinder and plane waves around it. So formally, the problem now kind of looks like an interacting 1D fermion chain, just with a very complicated 4 fermion interaction coming from the Coulomb. But we can take that very complicated Hamiltonian, treat it as a 1D fermion chain, and then solve it using this amazing numerical method called the infinite density matrix renormalization group, which essentially gives you semi-exact numerical simulations or solutions for the ground state and excitations of any 1D fermion or spin chain. The basic technology here is it's a variational ansatz where you assume that the ground state is well represented by this matrix product state, and there's nice rigorous results that show as the size of these matrices become large, you can recover any phase of matter that has a 1D area law, and then we use it as a variational ansatz. Yeah.
In the introduction, we were talking about anomalous quantum Hall.
Yeah. Yeah, but it's kind of important that you do it at where is it? Yeah, you do it in a limit where there's 1 flux per unit cell. So there's no like in the end, you have, a lambda level is a Chern 1 band. We don't usually think of it that way, but you could go to a plane wave basis with a magnetic Brillouin zone, and it's a Chern 1 band. So this is a Chern 1 band with dispersion and interactions. The special thing you get from a Landau level is that the Berry curvature of this Chern 1 band is perfectly uniform, whereas in MOT2, there's going to be some variation in the Berry curvature. So it's been argued, like in the limit where you go to small twist angle, it's supposed to become fairly flat. At 3.8 degrees, there's actually some variation. So we're mainly just considering the effect of the dispersion, but I don't know that qualitatively dispersion and some degree of Berry inhomogeneity aren't necessarily that different. Yeah, but we're not trying to be super microscopic about the energetics of the MOTE tube. It's more conceptual. So with DMRG, we can find the ground state, and then I want to be able to convince ourselves or you that it's a superconductor. So what do we measure? Well, because we've taken the 2D problem and mapped it onto effectively a 1D problem, the charge U1 symmetry can't be spontaneously broken. Instead, what we can get is algebraic off-diagonal long-range order. So if we define a pair operator which makes a Cooper pair, what we want to look at is the two-point function of the Cooper pair, and we should be able to see that in the superconducting phase, you find power laws with some well-defined exponent. So these are algebraic charge-to correlations, where the electron correlations should be gaps, so they should be exponential, and these are kind of the two signatures of a superconductor. So in a sense, this is, in our case, it's sort of an analog of looking for the well-known Luther-Emery liquid, but there you're considering spin. In our case, we're taking a 2D problem and putting it on a cylinder. So we have a cylinder, or sorry, we have a Fermi surface in 2D that then has its momentum in the y direction quantized by the circumference. So it's like a Fermi surface that gets cut, and you have some discrete ky modes. So it's like instead of the spin of the Luther-Emery liquid, we instead have momentum, and you're looking for a phase which has a gap for the excitations which carry momentum, but not for the charged two ones which are neutral. And the clear signature of finding a superconductor in the 2D limit, rather than just an artifact of a finite circumference, is we want to be able to show that the power law of this, you can show through some simple bosonization argument that you should be able to find that the exponent of it decays as 1 over the circumference of the cylinder, where the number there is related to the stiffness and velocity of the superconductor, the phase mode of it. So here for an example is an example of a point that we believe is in the superconducting phase. This is just showing what are the correlation functions for pairs. And as we converge the DMRG, which is taking these curves and going to darker colors, basically using larger matrices, we see the numerics converge to a power law that we can do a scaling analysis to extract as, say, 1 over the 0.9. So that's showing that we have this algebraic off-diagonal long-range order with a given exponent. And what we can do is, once we can then measure that exponent, we can ask, what is the exponent as you change the strength of the Moiré potential? You go from the gapped phase, which is just fractional quantum Hall, where the infinite is the exponent's infinite. There it's actually exponential decay. Then you enter into the superconducting phase, where you can have a quite small exponent and then eventually enter into the metal. And the key thing is, if we do 2 different circumferences, you can see that the exponent gets smaller, roughly in proportion to what we would expect that it should go as 1 over Ly. So for example, from 5 to 7, the exponent goes down by 0.6, and 5 over 7 is what, 0.7. So it's actually becoming a superconductor about at the rate you expect. So in 2D, we would hope if we could keep going to larger circumferences, this curve would just keep coming down here, and that would be a true 2D superconductor, whereas in the metal, you don't see that same scaling. The other thing I needed to show is that there's a charge gap. So at least in this study, we didn't directly measure energetics, so it's something we could do in the future. So instead, let's just look at the correlation function, the electron-electron correlation function, and we can calculate what is the exponential decay of the electron-electron correlation function. Because we're doing a numerical method, we need to converge the numerics, and what we find is this curve here is the correlation length of the electrons, and we see as we converge the numerics, it bends over and appears to converge, whereas the correlation length for charge 2 objects is here, keep just diverging like a power law. So this is basically charge 2, power law, charge 1, the fermion's exponential decay. So we can look at what are these correlation lengths as a function of the Moiré potential. And again, we see you go from all correlations are super small in the quantum Hall state. Then in the superconductor, you have a finite correlation length for electrons, but a very large correlation length for the charge 2 things, and in fact diverges as you converge it. That's the off-diagonal long-range order. And then in the metal, you find that actually everything is large and diverges as a power law as you converge the DMRG. Okay, so that's then how we figure out this phase boundary. So what is the pairing symmetry of the superconductor? Let me show you two things here. This is just showing what is the occupation of plane wave K in the many-body state. If I went deep into the fractional quantum Hall, you would find that you're 2/3 occupied everywhere. It would be perfectly flat. There'd be no K response. Then as you turn on the dispersion, the fractional quantum Hall distorts a little bit, and some of the charge transfers from the gamma point to here, because it turns out that for this potential, it's repulsive here and attractive here, so it kind of wants to have a hole-like pocket. But the fractional quantum Hall state is gapped, so you see just a smooth evolution of the number as you go across here, consistent with there just being exponential decay of the electron correlations. There can't be any sharp singularities. When you enter into the superconducting state, you see it being much closer to being like a Fermi surface, but it's not a drop, a perfectly sharp drop here. It's smeared out over a little bit, which is the coherence length of the superconductor, which in the previous plot we actually show is finite because we showed that the electrons are gapped. So you can't have a Fermi surface here either. It's just smeared out over a little bit. And then next is a kind of cool technique in the numerics where we can use the asymptotic form of the Cooper pair correlation function to compute a proxy of what is the pair function. So what's the expectation function, the wave function for the Cooper pair as a function of momentum. And what you can then see is that in the fractional quantum Hall state, there's no strong signature in the pair wave function as you approach the Fermi surface, whereas in the putative superconductor, you see a big peak in the pair wave function around the Fermi surface, and the color of it indicates the phase. You can actually see here that the phase winds around by 6 pi. So this is basically consistent with something like a weak coupling F plus IF superconductor here. Okay. So I think that's, what was that? It's a whole Fermi surface. So the outside, we're at 2/3 filling, and it's basically filling 1 everywhere and then filling 0 here. So hopefully I haven't made a sign error on the next slide, but maybe you can correct me, because when we want to compute the Chern number of the superconductor, we're going to need to know which way does it wind, and is it a hole or electron surface? So maybe Senthil's about to correct me on the fly. We'll see. But okay, so we want to know, we have a topological superconductor, or we have a superconductor. What is the topology of the superconductor? Physically, this would correspond to the superconductor can have some number of chiral Majorana modes at its edge, how many of them and what are their chirality. So the calculation we want to do here in the weak coupling picture would be to compute the Chern number of the BDG bands. And the formula we can use is, normally we'd say that the Chern number is basically just the angular momentum of the condensate, which we found is 6 pi winding. That's L is equal to -3. But because this is a whole pocket starting from a Chern 1 band, you need to start from the Hall conductance of integer quantum Hall, which is 1. And so I believe it is then 2C, like 2 minus 3. So the net result we think should be that you have -1 Chern number, which means there's 1 Majorana mode at the edge. So it's a strong topological superconductor. And the implication in the bulk would be that if you introduce superconducting pi vortices, they would carry an odd number of Majorana modes. So they'd have non-abelian statistics. Okay. Any sign errors? I think it's okay. Yeah. I mean, no matter what, it's odd. Yeah, no matter what, it's odd, which is probably the important thing here. Okay, so summary of the numerics. We find evidence that at least at 2/3, there seems to be a phase transition from quantum Hall to superconductor to metal. Though I'll admit, while we put it in the paper, I'm glossing it over here. There is close competition in the superconductor between a superconductor and a reentrant integer quantum Hall state, which is basically a charge density wave that carries Hall conductance. And interestingly, in the experiment, when they dope this fractional quantum Hall state, on one side they see a superconductor, and on the other side they see a reentrant integer quantum Hall state. I will tell you about that. Yeah, given that that was my whole motivation. Okay.
Of variation with Morey potential. Why is this the way the phases are?
Okay, well, so at no Morey potential, we started out with a Landau level and Coulomb repulsion. So it's like totally plain vanilla Laughlin state. Very strong Morey potential. You just have a dispersive band and it would become a metal. So the interesting thing is, yeah, you're asking what's the intuition for it being a superconductor? I don't know. Before either the experiment or the numerical experiment, I wouldn't have told you it was going to be a superconductor. So I don't have too much intuition. I mean, it could be, the weak pairing. So eventually the superconductor, if you measure a point here, it basically looks like a weak pairing superconductor. There's almost a Fermi surface, and there's just pairing right at the Fermi surface with a coherence length of like 20 Morey lengths. Like it's fairly weak pairing. So, I said there was these two theoretical pictures. One would be starting from the metal and then asking about like Kohn-Luttinger mechanism or something and the interplay with the quantum geometry. That would be this point of view here. Because I'm speaking to UQM, I'm of course going to start here and ask whether this is QED3, at the transition. As far as doping it, we haven't published something on this yet. I think it's quite delicate. The reason we've drawn it this way is we can't look at that many different dopings, but it sort of seems like what happens is that we call it FCI here because you dope it, some anions enter into it, and then they appear to form like a Wigner crystal of anions. It's not that surprising. But eventually, the anions disperse as you turn on the Morey potential, and then they can enter into a liquid state. And there seems to be some evidence that the boundary between that anion crystal and the liquid state comes down with the amount of doping. So, if we wanted to say, oh, we've explained the experiments, the idea would be the experiment is at a particular VM, where at 2/3 you get the fractional quantum Hall. But then as you dope it, you move this way, and because this phase boundary comes down, you can then have the FCI, a plateau, and then the superconductor. So that would be the potential explanation, but I'm not claiming to do anything very microscopic here. This isn't the precise model of MOT2. Yeah. Oh, yeah. Mm-hmm. No, it changes what the critical, it changes the critical point for sure. So as a function of the gate distance, if the gate distance is really close, it kind of becomes the contact interaction and becomes very far away. You see the region of the superconductivity shrinks, which probably makes sense. And actually for pure Coulomb, I'm not sure we see a superconductor, but for the sort of gate seen in the experiment, like a gate 50 nanometers away, there's still a regime which we think is superconducting. But quantitatively, it does make a difference. Yeah. Okay, so what's the nature of the phase transition? I would like to say more, but this is currently in progress. It's at least either continuous or very weakly first order. We'll need to do more work to see. So for example, let's look at the occupation of plane wave state K, N of K. In the metal, it would go from 0 to 1 to 0. You'd have a sharp Fermi surface. In the quantum Hall, it would just be uniformly 2/3. This is showing the 2D version of it. And as you change VM, what you see is just a continuous evolution of N of K. Well, it's largely continuous evolution of N of K from being constant to then showing the Fermi surface. So for example, this is a zoom in of taking one cut, say here. What is N of K of this particular mode? And this here is zooming in near the transition from what we think is the quantum Hall to the superconducting side. And this is in progress. We need to obviously have like finer resolution data, but there's no obvious sign of a first order transition so far. So for the moment, let's assume it's continuous, but we're going to have to understand this better. So going back to the theoretical expectation, weak coupling, or is it strong coupling? Let's evaluate, on the first couple slides, I said there is actually a way QED3 could describe a phase transition from 2/3 quantum Hall to the superconductor. Let me just review that parton construction again. So the basic idea is I'm going to take the electron, and rather than writing as F1, F2, F3, the F1, F2 I'm just going to write as B. It's equivalent, but in this case it's simpler to just think about it this way. So a regular BF parton construction. And the way you describe the 2/3 state in this picture is F you put into a Chern 1 band that does flux attachment. You think of B as the composite bosons, and via the usual manipulations, you'll find that those composite bosons are actually at filling factor 2. So the B can then enter into the bosonic integer quantum Hall state. So this is an alternative way about thinking the usual composite fermion picture. That's another way you can do the partons, but this is how I'm going to discuss it here. So then when we ask what's the effective theory for this, bosonic integer quantum Hall gives Chern number of 2, and it couples to the emergent gauge field. And then the thing that was doing flux attachment, the F, we have in a Chern number 1 state. So this is the description of 2/3 quantum Hall in this language. And what I'm going to imagine is that the F undergoes a phase transition, a band inversion. And when you look at the symmetry, so this is analyzed carefully in Darius's and Senthil's paper from last summer, I guess. You find that there'll be a threefold band touching, so it becomes generic for the Chern number to change by 3. And then when you put in that the thing that was doing flux attachment is actually -2 flux attachment, you find that there's no Chern-Simons term for the emergent A, and then the emergent A actually Higgses out the physical gauge field, and this is a description of a superconductor. So I'm short on time, so this will be a bit brief. Okay, so we have a potential description of a 2/3 to superconducting, and it would be described by NF equals 3, QED 3, coupled to a Chern-Simons term. So that'd be cool to see, but there's a contradiction, because if you keep track of the chiral central charge in that description, you'll find that the superconductor actually has 4 Majorana modes at the edge, whereas our result is consistent with 1 Majorana mode at the edge. So it doesn't actually look like that description is possible. So I was just discussing with Senthil this morning, it may be that there's actually a more complicated parton description that you can ask him about. I think will be interesting to understand better, where you can actually have a different, distinct superconductor, which would have an odd number of Majorana modes. So now I'm excited to see if we can compare the superconductor against that and see if that's might be what's happening here. Or it could have nothing to do with the quantum Hall state, we don't know. But the fact that it seems at least weakly to be seems like a continuous phase transition is reason to keep thinking about it. So that, thank you.
Right, questions?
You know, in theory, as you say, just threefold degeneracy. But in your numerical calculation, do you see any pattern of the repeated? Because I'm surprised you have a single hole pocket in the middle, which is usually because interference with anion with background charge. There's a mini band structure, and your numerics don't have that.
Well, we need a way to measure the parton band structure. So what we need to do, and we could do this, would be add 1 anion and then measure its dispersion relation. So I think that'd be a very fun calculation to do, and we'd be able to do it in DMRG, so that'd be an exciting thing to do. So that'd be fun if we can actually see the threefold, it will have to be there, the threefold thing, and whether we can see the band gap of the partons closing in some way. That would be exciting.
Fermi surface may be compatible with a threefold degeneration parton, or maybe they are incompatible.
It's compatible. It follows when you keep track of the magnetic algebra that there can be no magnetic algebra for the electrons, but at 2/3 filling, you know, the average mean fields of everything still give you the threefold. Yeah.
Can you remind me again, do you have C6 symmetry or just C3 symmetry?
We had C6. So Tiger's also looked at breaking the C6 down to C3. The superconductivity is at least stable for a little bit. Eventually, the C3 is like like in the weak coupling picture, because it's a chiral superconductor. Oh, are you asking about breaking C2 or breaking C3? We have C6. The actual material has C3. So what we looked at was breaking C2. Yeah, and that's important because this is pairing with this. There's no spin. This is spinless. So like breaking C2 and having a triangular Fermi surface is like pair breaking. And I think we eventually see that it's bad for the superconductivity, but it seems to survive a little bit of the anisotropy.
Hall state, nothing happens. Yes.
I don't, we probably didn't check. Where's Tiger?
Yeah,
is killed, superconductivity is killed.
As you move away from exact two-thirds filling, do you expect the superconducting phase to go down to lower more potential strength, or what's the expectation?
Lower.
Epsilon, just a little bit of doping around.
You're just asking whether it comes down or goes up here?
Essentially.
Well, this expectation would be not backed by any numerics whatsoever, but I would like to expect that it goes down. Let me put that, but I mean, maybe there's actually several people have been working on this idea of anion superconductivity, and the expectation, I think, if you think about adding VM to that phase diagram, would be that it would come down. Yeah.
So if you take the anion superconductivity picture, right, that is the, you have, let's say you can increase doping, right? So you put a gas of charge 2/3 anions.
Yeah.
What the superconductor do you expect to get? Like what?
It's the one I described, because basically they're just two different ways of changing the Chern number of one of the partons. Yeah, so the idea is you want to change the Chern number of one of the partons. This is not the description, but you're changing the Chern number of this parton from 1 to -2. One way to do it would be what we're describing. It's not doped, but you have band inversion. The anion superconducting way is you instead change the chemical potential of that parton. But when you do it, it actually breaks this upper band into like lambda levels. And then the total Chern number of the third parton changes from 1 to -2. In exactly the same way as I assumed band touching changed the dispersion from 1 to 2. So on the other side, you get the same superconductor. Yeah. Mm-hmm. Yeah.
And what happens to topological order as you go from the fractional quantum fold to the superconductor? Do you like lose the anion statistics?
Yes, certainly yes. I mean, we actually haven't confirmed, I guess, that the superconductor isn't fractionalized, but like for that field theory of the description, which I guess is actually wrong, but like in that case, you get a non-fractionalized superconductor. But we actually haven't verified that the superconductor we're looking at isn't fractionalized, but I'm almost certain it's not, because you can see eventually just seems to become a weak pairing superconductor and then smoothly goes to the metal. So I doubt it's fractionalized. It's probably just BCS.
Let's